Welcome students in the lecture series of some basic concepts of real analysis. In the last lecture, we discussed about density theorem, open and closed intervals, sequences, limit of sequences, bounded sequences and geometrical interpretation of bounded sequence. Now, in this lecture, we will discuss some important theorem of sequences. Our first result is, let x is equals to xn and y is equals to yn be a sequences of real numbers that converges to xn, y respectively, and the sequence xn is less or equals to sequence yn for all n belongs to the natural number. Then we have limit of xn is less or equals to limit of yn, that means x is less or equals to y. Let us start with the proof. As given, limit of xn is equals to x and limit of yn is equals to y. Say this is our equation number 1 and this is our equation number 2. Now let us consider the sequence zn. Zn is equals to yn minus xn. So that we can say that z is equals to zn and zn is equals to sequence y minus sequence x, and we know that zn is greater than or equals to 0 for all n belongs to natural number. Let us recall the result. Let x is equals to xn and y is equals to yn be a sequences of real numbers that converges to x and y respectively. Then the sequence x minus y, which is equals to xn minus yn, must converge to x minus y. Now apply this result, we get limit z is equals to limit zn and limit zn is equals to limit y minus limit x. Say this is equation number 3. Now again recall some result. Let x is equals to xn is a sequence of real numbers that converges to x and xn is greater than or equals to 0 for all n belongs to the natural numbers. Then we can say that the limit x must be greater than or equals to 0. Hence, from the above result, we can say that limit of z is greater than or equals to 0 as given zn, the sequence zn is greater than or equals to 0. Hence, from the equation number 3, the equation number 3 says that limit of z is equals to limit of x minus limit of x. We can say that this is equals greater than or equals to 0. That implies limit xn must be less or equals to limit yn. Now, moving towards next result, our next result is let x is equals to xn is a convergent sequence of real numbers that converges to x, and if a is less or equals to xn and xn is less or equals to b for all n belongs to natural number, then we have a is less or equals to limit of xn and limit of xn is less or equals to b. Let us start with the proof. As given, the sequence is convergent, hence we can easily derive our equation number 1. Equation number 1 says that limit of xn is equals to x. Now consider the constant sequences. The sequence a can be written as a comma a up to so on, and the sequence b similarly can be written as b comma b up to so on are the constant sequences, and we know that the constant sequence converges to itself, since we can say that limit of a is equals to a and limit of the sequence b is equals to b. Say this is our equation number 2. Now recall the result. Let x is equals to xn and y is equals to yn be the sequences of real numbers that converges to x and y respectively, and xn is less or equals to yn for all n belongs to natural number. Then we must have limit xn is equals to limit yn. Now apply this result, we get a is less or equals to xn and xn is less or equals to b. If we apply limit, then we get limit a is less or equals to limit xn and limit xn is less or equals to b. And from equation number 2, we get limit of a is equals to a and limit of b is equals to b. if we substitute the value of equation number 2, then we get a is less or equals to limit of xn and limit of xn is less or equals to b. Now, moving towards next result, our next theorem is squeeze theorem. The statement for the squeeze theorem is, let x is equals to xn, y is equals to yn and z is equals to zn be a sequences of real numbers such that xn is less or equals to yn and yn is less or equals to zn for all n belongs to natural number, with limit xn is equals to limit zn. Then we have y is equals to yn is convergent and the limit for all the sequences are same, that is limit of xn is equals to limit of yn and the limit of yn is equals to limit of zn. Now, let us start with the proof. As given, xn and zn are convergent sequences and both the limits are same. So, limit of xn is equals to limit of zn and let us say both the limits are w. So, limit of xn is equals to limit of zn and the limit of zn is equals to w. Then by the definition of convergence of sequence of real numbers, we get for every epsilon greater than 0, there must exist a natural number k depending upon that epsilon such that modulus of xn minus w is less than epsilon for all n greater than or equals to that natural number. Similar way, modulus of zn minus w is less than epsilon for all n greater than or equals to k. Say this is our equation number 1. Now, by the given hypothesis, we can conclude that xn minus w is less than yn minus w and yn minus w is less than zn minus w for all n belongs to natural number and n is greater than or equals to k. Using equation number 1, we can say that minus epsilon is less than yn minus w and yn minus w is less than epsilon for all n greater than or equals to that natural number. Since epsilon greater than 0 is an arbitrary, so this implies that modulus of yn minus w is less than epsilon for all n greater than or equals to k. That is, we can say that limit of the sequence yn must be equals to w. The geometrical interpretation of the squeeze theorem is, imagine three functions f of x, g of x and h of x graphed on the same coordinate plane. The squeeze theorem states that if gx is always between f of x and h of x, that is f of x is less or equals to g of x and g of x is less or equals to h of x for values of x near a certain point c, and if both f of x and h of x approaches the same limit L as x approaches towards c, then gx must also be squeezed to the same limit L as x approaches towards c. As we can see in the diagram, the function f of x is squeezed between g of x and h of x, both approaching the same limit L. Now, our next result is, let x is equals to xn is a convergent sequence of real numbers that converges to x, then the sequence modulus of xn of absolute values converges to mod x. That is, if x is equals to limit of xn, then we must have mod of x is equals to limit of mod xn. Now, as given, xn is a convergent sequence and converges to x. So, we can easily derive our equation number 1. Equation number 1 says that limit of xn is equals to x. Now, by the definition of convergence of sequences of real numbers, we can say that for every epsilon greater than 0, there must exist a natural number k depending upon that epsilon such that modulus of xn minus x is less than epsilon for all n greater than or equals to k. Say this is our equation number 2. Now, recall the result for absolute values. let a and b are any real numbers, then we have modulus of mod a minus mod b is less or equals to modulus of a minus b. Now, applying this result, we can say that modulus of mod xn minus mod x is strictly less than modulus of xn minus x for all n greater than or equals to k. Hence, from the equation number 2, recall the equation number 2. Equation number 2 is modulus of xn minus x is less than epsilon for all n greater than or equals to k. So, from equation number 2, we can say that modulus of mod xn minus mod x is less than epsilon for all n greater than or equals to k. Hence, by the definition of convergence of sequences in real numbers, we can say that limit of mod xn is equals to mod x. Our next result says that let x is equals to xn be a sequences of real number that converges to x, and suppose that xn is greater than or equals to 0. Then the sequence under root xn of positive square roots converges, and limit of under root xn must be equals to under root x. As given, x is equals to limit of xn and this is greater than or equals to 0. So, the following assertions make the sense. Now, we consider two cases. Our first case is x is equals to 0 and the another case is x is greater than 0. Now, consider the case 1. Case 1, if x is equals to 0, let epsilon greater than 0 be given, and by our assumptions we can say that xn approaches to c or limit of xn is equals to 0. Then by the definition of convergence of sequences in real numbers, we can say that for every epsilon greater than 0, there must exist a natural number k depending upon that epsilon such that 0 is less or equals to xn, and xn can be written as xn minus epsilon, and we can say that by the choice of epsilon this is less than epsilon square for all n greater than or equals to k. If we rewrite this equation, then we get 0 is less or equals to under root xn and under root xn is less than epsilon for all n greater than or equals to that natural number. Since epsilon is arbitrary which is greater than 0, so this equation can be written as modulus of under root xn minus 0 is less than epsilon. Again, by the definition of convergence of sequence, we can say that under root xn approaches towards 0 or limit of sequence under root xn is equals to 0. Now, consider the case 2. Case 2 is if x is strictly greater than 0. As x is strictly greater than 0 and x is real number, then we can say that under root x is also greater than 0. Now, for any epsilon into under root x greater than 0, we can say that by our assumptions xn converges to x. There must exist a natural number k depending upon that epsilon such that modulus of xn minus x is less than epsilon into root x for all n greater than or equals to k. Say this is our equation number 1. Now, consider the equation under root xn minus under root x. Our first step is rationalize this term. After rationalizing, we get under root xn minus under root x is equals to xn minus x upon under root xn plus under root x. Say this is our equation number 2. Since under root xn plus under root x is greater than or equals to under root x, and as we know under root x is strictly greater than 0, this implies that 1 upon under root xn plus root x is less or equals to 1 upon under root x. Say this is our equation number 3. Now, substitute the value of the equation 3 in equation number 2. Recall the equation number 2. Equation number 2 is under root xn minus under root x is equals to xn minus x upon under root xn plus under root x. If we substitute the value of equation number 3 in equation number 2, we get modulus of under root xn minus under root x is equals to modulus of xn minus x upon under root xn plus under root x. This term is less or equals to 1 upon under root x from equation number 3 into modulus of xn minus x. Say this is our equation number 4. Equation number 4 is modulus of x under root xn minus under root x is less or equals to 1 upon under root x into modulus of xn minus x. Now, substitute the value of equation number 1 in equation number 4. Now, recall the equation number 1. Equation number 1 says that modulus of xn minus x is less than epsilon times root x. So, substitute the value of equation number 1 in equation number 4, we get modulus of under root xn minus root x is less than 1 upon under root x into epsilon times under root x for all n greater than or equals to that natural number, say k. This implies that we get modulus of under root xn minus under root x is less than epsilon for all n greater than or equals to k. Again, by the definition of convergence of sequence of real numbers, we can say that the limit of the sequence under root xn approaches towards under root x. Now, our next topic is monotone sequences. For this, we have some basic theorems. For that theorems, the definition is let x is equals to xn be a sequence of real numbers. We say that x is equals to xn is an increasing sequence if it satisfies the following inequality. That means x1 is less or equals to x2 and x2 is less or equals to x3 and up to so on. For example, first sequence is x is equals to n for all n belongs to natural number. Say x is equals to n and n belongs to natural number, then the sequence can be written as 1, 2, 3 up to so on. We can easily check this is an strictly increasing sequence. Our second example is x is equals to 2 to the power n for all n belongs to natural number. If we expand this sequence, we get 2, 4, 8, 16 up to so on. Again, we can easily see that this is our increasing sequence. Our next definition is decreasing sequence. Let x is equals to xn be a sequence of real numbers. We say that x is equals to xn is decreasing sequence if it satisfies the following inequality. That is, x1 is greater than or equals to x2 and x2 is greater than or equals to x3 and up to so on. For example, first sequence is x is equals to 1 upon n for all n belongs to natural number. If we expand this sequence, we get 1, 1 upon 2, 1 upon 3, 1 upon 4 and so on. So, we can check this inequality. First term is greater than the second term, the second term is greater than the third term and so on. Our second sequence is x is equals to 1 upon 2 to the power n for all n belongs to natural number. Again, if we expand the sequence, we get the sequence of the form 1 upon 2, 1 upon 4, 1 upon 8, 1 upon 16 and so on. Again, we can check that first term is strictly greater than the second term and the second term is greater than the third term and so on. So, these kind of sequences are known as decreasing sequences. our monotone sequence is either increasing or decreasing. We say that a sequence of real number x is equals to xn is monotone if it is either increasing sequence or decreasing sequence. Now, let us start with the monotone convergence theorem. For that, the statement is a monotone sequence of real numbers is convergent if and only if it is bounded. I repeat, a monotone sequence of real numbers is convergent if and only if it is bounded. Further, if x is equals to xn is bounded increasing sequence, then we have limit of xn is equals to supremum of the set, and the set is defined as xn for all n belongs to natural number. And second part is, if x is equals to xn is bounded decreasing sequence, then limit of yn is equals to infimum of yn, such that for every n belongs to n. I repeat this statement for monotone convergence theorem. Monotone convergence theorem states that a monotone sequence of real numbers is convergent if and only if it is bounded. Further, if xn is bounded increasing sequence, then the limit of xn is equals to supremum of xn. And if x is equals to xn is bounded decreasing sequence, then the limit of yn is equals to infimum of yn. Now, let us start with the proof. Let us suppose that x is equals to xn be a monotone convergence sequence of real numbers which converges to x, where x belongs to real number. We need to show that x is equals to xn is bounded sequence. As given, x is equals to xn is monotone convergent sequence. Let us suppose a sequence x is equals to xn converges to x, that is limit of xn is equals to x. Now, by the definition of convergence of sequence in real numbers, we can say that a sequence x is equals to xn in real numbers R is said to converge to a real number x, or x is the limit of xn if for every epsilon greater than 0, there exists a natural number k depending upon the epsilon, such that for all n greater than or equals to k, then we must have modulus of xn minus x is less than epsilon. So, using this definition, we can assume our epsilon is equals to 1, which is greater than 0. Then, by the definition of convergence of sequence, there must exist a natural number k depending upon that epsilon, that means depending upon 1, such that we have our equation number 1. That is, modulus of xn minus x is strictly less than 1 for all n greater than or equals to k. Now, if n is greater than or equals to k, consider the equation mod xn. Say this is our equation number 2. If we add and subtract x in equation number 2, we get our equation number 3. Equation number 3 says that mod of xn minus x plus x. If we apply triangular inequality in this equation, we get our equation number 4, that is mod xn is less or equals to modulus of xn minus x plus x. Now, substitute the value of equation number 1 in equation number 4. This is our equation number 4. Equation number 4 is modulus of xn is less or equals to modulus of xn minus x plus mod x, and our equation number 1 is modulus of xn minus x is less than 1. If we substitute this value in equation number 4, we get modulus of xn is less than 1 plus mod x. Now, if we set capital M as supremum of the set, and the set defined as modulus of x1 comma modulus of x2 up to modulus of xk minus 1 and the term 1 plus mod x, then we can easily say that our sequence, that is mod of xn, is less than or equals to m for all n belongs to natural number, that is our sequence is bounded. In today's lecture, we discuss some theorems related on sequences and their limit. We also discussed Cauchy sequence, monotone convergence sequence and their properties. In next lecture, we discuss some theorems related on Cauchy sequence. Thank you.